Hello advanced physics students, this is Dr. Brenzi and this is lesson 8.2.3. In this lesson we're going to be able to define an amp and an ohm and use those to solve physics problems. Those might be terms that you might have come across at some point, maybe if you work with electronics or maybe even working with cars that you might have come across these, but in physics we have some definitions for those, but we're going to find out what those are in this lesson, so let's go ahead and begin. Now, if you take a wire, and usually it has to be a metal wire. Some metals work better than others, but if you take a wire and you connect the ends of it to a battery, there is going to be a difference in electric potential between those two ends of the wire. And when we were talking about voltage or electric potential, and I actually brought out a AA battery from one of my remote controls, what we learned is that this is at a electric potential or voltage of 1.5 volts, and we could think of this electric potential V as being at 0 volts. So there is a difference in the electric potential between the two ends of our wire here. Well, if that happens and our wire has been chosen to be a good wire, then we're going to observe that electrons flow. Now, there's a reason I drew two circuits on here. Back in the day when people were starting to first do research on this stuff in the 18th century, they had no idea of what an electron and what a proton were. As a matter of fact, people like Benjamin Franklin thought that this stuff was like a fluid, like it's a fluid traveling through a pipe. And to some degree, they were right, but not really. They had to actually kind of guess as to what was going on. So they actually decided on something that had a positive charge, and then another thing had negative charge. And I think I mentioned that before, but they decided that we're going to say that the positive charge is the thing that does the flowing. Okay, so we're actually going to give this flow a different name here in a second. This is what they thought in the 18th century. And because that's when we started doing research on this stuff, that kind of stuck. So we almost think of, when we talk about electric circuits, we almost think about this flow traveling from positive to negative, or from high electric potential to low electric potential. Now, when we started to learn more about electrons and protons and which one had which charge and which one actually does the moving, and we found out it's actually the electrons that do all the moving, well, there was a big problem because we know that electrons start on this end of the terminal because they have a negative charge and they want to actually flow this way, and those are the things that are actually doing the moving. So, electrons start off at the negative charge and they actually flow in the opposite direction of what they thought happened in the 18th century. So this is what really happens. But because a lot of the people in the 18th century, were making the rules up about how electricity works, we still talk about current. Well, hey, I didn't mention the word current. This flow going in this direction from positive to negative. And as a matter of fact, I kind of spoiled my next slide here. Because that word for flow is current. So the definition of current is the total amount of charge that flows through a point on a wire per second. So if I were to quickly glance back at this wire here, or at my circuit, okay, and if I were to pick a point on that circuit, let's say right here, well, actually, let me go right here instead, okay. So if we were to pick a point along that wire, let's say right here, okay. That's too small for you guys to see here. Let me draw a bigger arrow. Okay, so we pick a point on the wire. And let's say that we'll make that our point. So this is the wire. What we're going to do is we know that electrons flow. And as they flow, they come across the point that we're interested in, that we're looking at. And maybe I should erase this red arrow and replace it with an eyeball to kind of remind us that we're looking at this thing. Okay. And here comes the eyeball. And there we go. Eyeball. Okay, so it's an eyeball looking down, and if we had a machine that would count the number of electrons or the amount of charge that flows through here, then we would be measuring current. So current is the amount of charge that flows through a point on a wire per second. So it's charge per second. We usually call this current I. It's usually given the variable name capital I. And its units are coulombs per second. Okay, but we actually give that a special unit, that unit a special name, in honor of André Marie Ampère, who did a lot of research on electric current. And in his honor, we call the unit of current an ampere, or an amp for short. So if you look at a fuse on you, or a circuit breaker on your house, if you've ever looked at a circuit breaker in your house, or if you've ever looked at, the technical details of any piece of electronics, it will say, it might say 1 amp, or it might say 50 milliamps. That is describing to you how much current flows through that device, how much charge flows through that device per second. Now, when current flows through a wire, some of the current is lost. Some of the electrons, they lose their way. Well, how do they lose their way? They lose their way by colliding with atoms that exist in the wire. So you could imagine like this wire being like a tube, and in this tube, we know that of course this tube is made up of atoms, right? Atoms, so we could put a bunch of atoms in here, and you can just draw random atoms in here. I mean, it's packed with a lot of atoms, right? Now, the electron is not going to be affected by every atom in here, but if I have an electron, and let's start it from the right, since that's the way our current was going, or electrons were going. So let's say an electron goes this way. There are electrons that, make it through all the way through the wire and keep going. A lot of them might do that. And they might get to the other side and say, yay, I made it through. But there are some electrons that interact with an atom and they go smash and they no longer flow. Well, this is resistance. The wire is resisting this current flowing through it. Okay, and there are some things that resist current more than others do. In physics, we call materials that allow electrons to flow almost freely, we call those conductors. So a conductor, examples of good conductors are copper, to a lesser extent aluminum, and those are the things that you will see household electronic circuits made out of, are those two items. Okay. There are materials that are very good at resisting the flow of electrons. Those are called insulators. So an insulator, some ceramics are good insulators. Rubber is usually a good material that insulates. Those are examples of insulators. And then there are materials that are kind of in between, and we call those semiconductors. Silicon makes a good semiconductor, and so does another element called germanium. So those are examples of semiconducting materials. Okay, so we have things that allow electrons to flow, and we have things that stop electrons from flowing very well, and then we have some things that are in between. Now, we actually give resistance a number. There is a number that we can calculate for the amount of resistance of a wire, and it's given by this the formula right here. R represents resistance, and that is equal to something called resistivity. Now, resistivity depends on the material that you're looking at. So this would be a number that you'd have to look up in a table for different materials. So a conductor will have a very low amount of resistivity. And by the way, that letter is the Greek letter rho. It kind of looks like a P, but it's not actually a P. It's actually the Greek letter rho. That is low in conductors. And it's very high in insulators. And if you think about that, that makes sense because, because conductors have low resistance. I can't think and talk at the same time, or think and I can't think and write at the same time. that other statement might be true as well. So this resistivity is low in a conducting material and high in an insulating material. The resistivity also depends on the length of the wire. Now, the reason behind that is because if I make this wire longer, that means that the electrons have to dodge more atoms, or they have to avoid more atoms in order to be able to successfully get through the wire. So the longer you make a wire, the more resistance it has. On the other hand, the bigger the cross-section area of the wire, the less resistance you will get, because you now have more electrons available to actually move through the wire. Okay. So if we were to make this a larger diameter, we would end up making the area larger, which means we'd make the resistance of the wire smaller. You might have noticed in common household appliances that there are some things that have very skinny wires, and there are other things that have very, very thick wires. Now, the reason that you want a thick wire is because you want lots of area so that the resistance is low. in that particular wire. So things that you will plug into the wall have thick wires because you don't want to lose very much of the current, because the device that you're plugging in requires a lot of current. Whereas if you're like just plugging in your iPod, which doesn't use a lot of current, well, it doesn't need as much current, so you can get away with a smaller wire, which means the resistance of that wire would be, it's okay for that resistance to be higher. And that's my dog barking. Say hi to Molly, everybody. Okay, one last slide here, and then I'm finished. So the unit of resistance is called an ohm, and we give that unit of resistance a capital letter omega. You might recognize that from when we did oscillations, or actually simple harmonic motion. It's the same letter that's used, so and it's in honor of a gentleman whose name is Georg Simon Ohm, and he was a German physicist who did extensive research on resistance. So you might say that a wire, conducting wires usually have sorry about that, had to pause for a second here. So as I was saying, conducting wires usually have a resistance of about, I would say conducting wires are like nano ohms. Remember, nano means 10 to the negative 9. Okay. And usually insulators on, that sometimes you actually want an insulator in a circuit. Usually that will have ohms or kilo ohms, and sometimes with very large currents you can even have resistors that are mega ohms. So we know kilo means 10 to the 3, so 10 to the 3rd ohms. Mega means 10 to the 6th. So sometimes insulators provide a large amount of resistance compared to nano ohms, and nano means, of course, 10 to the negative 9. So there's a big amount of difference between the resistance of conducting wires and insulators. Alright, well, that's all I wanted to talk about today. So when we come into class tomorrow, we'll have a better idea of, we'll be able to actually work with current and resistance, and look forward to actually starting to talk to you a little bit about circuits. So I'll look forward to seeing you then. Bye.